Well, I want to thank the organizer for putting together this meeting and giving me the honor of being the first speaker. My topic will be related to cyclotomic polynomials and how they can be used to compute some generating functions. So let me start out with a theorem of McMahon from 1916. It says a number of partitions of a positive integer n for which no part appears exactly once equals the number of partitions of n whose parts are congruent to plus or minus 1 mod 6. Well, this is very straightforward to prove. The generating function for partitions for which no part appears exactly once is this product. It should be familiar to almost everyone here. For instance, if we choose this term x to the 3i, when we expand this product, that means that the part I appears 3 times. So we don't have an x to the I because no part is allowed to appear once. No part appears exactly once. Well, this sum is equal to this 1 over 1 minus x to the I, but with the x to the I missing. And we can rewrite it, put it over a common denominator, and then rewrite it in this form. Then we see when we expand this product in the denominator, we're going to have all the multiples of 2 as exponents, all the multiples of 3, but the multiples of 6 will appear twice, once as a multiple of 2, once as a multiple of 3, but one of those will be canceled out by the numerator. So we'll get exactly the exponents will be exactly the numbers that are not congruent to plus or minus 1 mod 6. So that proves this identity using generating functions. Well, why does this work out so elegantly? Well, in general, it's because cyclotomic polynomials are involved. The nth cyclotomic polynomial, Pn of x, I will define to be the polynomial whose roots are the primitive nth roots of unity. And I'm going to normalize them to have constant term 1. Usually they're monic. This only will make a difference when n equals 1, because otherwise the cyclotomic polynomials are monic and have constant term 1. So by a simple exclusion argument, the cyclotomic polynomial is this product d divides n, 1 minus x to the d raised to the power, the Mobius function of n over d. And the point is, for us, is that this is of the form of finite product of 1 minus x to the I raised to some integer power ai, positive or negative. So here's this note on the normalization. I'm going to take phi1 of x to be 1 minus x instead of x minus 1. Otherwise, nothing has changed. So in this proof of McMahon's theorem, the main point that made this argument work was that when we looked at this 1 minus 1 over 1 minus x, we remove just one term from the expansion, 1 over 1 minus x. This was a cyclotomic polynomial over 1 minus x. And that meant, since the cyclotomic polynomial is can be written in the form product 1 minus xi to the ai, we can write this expression in this form, and it turned out to be this. So when we take the product of f of x to the I over all I to get our generating function, we're going to get a nice product expansion. And you might say the second point is that when we do this, in this case, the numerator canceled the denominator of just in such a way that all we had was denominator factors. Each one that appeared had multiplicity 1. We get a very elegant combinatorial interpretation. Well, the fact that when we subtracted x from 1 over 1 minus x, we got this nice cyclotomic polynomial over 1 minus x. Suggests the following definition. A cyclotomic set is a subset S of the positive integers such that if we take 1 over 1 minus x and subtract from it those terms x to the j for which j is in S. So I'll denote this generating function by f sub s of x. We write it with numerator ns of x and denominator ds of x. We want both of these ns of x and ds of x to be finite products of cyclotomic polynomials. That is a cyclotomic set. It's rare that this happens, but we can think of S as a set of forbidden part multiplicities when we try to find the partition identity. And we take the product of f sub s of x to the I over all I. The elements of S are the part multiplicities which are not allowed to appear in our partition. But here's a more complicated example. S equals 1, 2, 3, 5, 7, and 11. Just coincidentally, 1 plus the first 5 primes. My fs of x is this, and if you work it out, somewhat of a miracle, but it's P6, P12, P18 over 1 minus x. And when we write it in this form of a product of 1 minus x to the i's, it turns out to be this. There's a 1 minus x to the 12th, 1 minus x to the 18th in the numerator, and the denominator has the exponents 4, 6, and 9. In this case, when we look at this product, f of x squared, f of x cubed, etc., we are going to have this nice kind of cancellation so that all the denominator factors have multiplicity 1, and the numerator is just 1. The numerator completely cancels the denominator, and the denominator factors, 1 minus x to the I, are for these values of I. Certain congruence classes modulo 36. So that leads to this, a new partition identity. For all non-negative integers, a number of partitions of n, so which no part occurs exactly 1, 2, 3, 5, 7, or 11 times. These are the excluded part multiplicities, equals the number of partitions into these parts satisfying star. Parts congruent in certain congruence classes mod 36. Here's a further example. We don't have to have S being finite for my definition. For instance, if S is all the positive integers except for 1, then this expression is certainly, well, it equals to 1 minus x squared over 1 minus x, or in other words, 1 plus x. We're only left, we've subtracted off all the terms here except for 1 and x. So certainly this is a product of cyclotomic polynomials, or a product of 1 minus x to the AIs. So what kind of identity do we get out of that? 1 minus x to the 2i product over 1 minus x to the I. From here, taking this expression, substituting x to the I for x and multiplying over all I, we get this cancellation, which leaves us with 1 minus x to the 2i minus 1 inverse. So we get the well-known and famous result of Euler, the number of partitions into distinct parts, because we've excluded all part multiplicities 2, 3, 4, etc. Every part appears at most once, equals the number of partitions of n into odd parts. So Euler's identity is part of this setup of cyclotomic sets. Well, it's very natural to ask, what are the cyclotomic sets? Well, the classification seems to be wide open. I don't know any simple description of them. We can say some nice properties of them. First of all, if we have a finite cyclotomic set, its maximum element is odd. That is a very simple proof. I guess since every talk should have a proof, we will write our 1 minus 1 over 1 minus x minus sum j and s, x to the j, as a numerator and denominator. Here, the denominator will just be 1 minus x because this sum is finite. And so s of x will be given by just rearranging this expression, 1 over 1 minus x times the sum of j and s, x to the j. So you can see the degree of ns of x is 1 plus the maximum element of s, this x times x to the j, where j is the maximum element of s. But the degree of every cyclotomic polynomial is even when n is greater than 2. So if we can show that ns of x isn't divisible by phi1 or phi2, then ns of x, which is a product of cyclotomic polynomials, will have even degree, and so the maximum element of s will have odd degree. But if you put x equals 1 or minus 1 in this expression, this second term will be even, and so ns of plus or minus 1 is 1. So it can't be 0. So we can't have the numerator divisible by phi1 or phi2. So that's the proof. The maximum element of s is odd. Well, one can also prove that Pn of x, I've shown it's not, when it appears in ns of x, n does not equal 1 or minus 1, and n is also not a prime power. That's a very simple proof too, but I think I'll skip the details here and go on to the third property, which is more important. For any number between 0 and the maximum element of s, which is I call d, exactly one of the numbers j and d minus j belongs to s. That means the cardinality of s is d plus 1 over 2. That gives another proof that d is odd. And again, this has a simple proof that's based on the fact that the cyclotomic polynomials have this symmetry. They read the same backwards as forwards. It's all that comes into it. Again, I will skip details, but it's a very elementary result. So here's a little table showing how many cyclotomic polynomials are there for a given value of the maximum element of s. So in other words, s has d plus 1 over 2 elements. Remember, d has to be odd, so here are all the odd numbers from 1 to 29, and the corresponding number of cyclotomic sets. Not so large. Maybe this is going a little bit more than linear. And I'm like d log d. If we just look at the sets s in P at positive integers, whose maximum element of s is d, and that has this symmetry property, there's 2 to the d minus 1 over 2 of them. So f of d is much less than the this trivial upper bound possible number of cyclotomic sets. Here they are for the maximum element of s less than or equal to 9. And there's 5 of them with maximum element is exactly 9. You can see some infinite classes, that is, some patterns. For instance, we always have 1, 2, 3, 3, 4, 5, 4, 5, 6, 7. etc. 5, 6, 7, 8, 9. Those are always cyclotomic sets. And there's a few more infinite families, but then there's some outliers, and I don't have a general result on what they look like. Let me make a little aside here from something that appeared in Math Overflow. So the symmetric polynomials, or that is palindromic polynomials of the form n(s) of x equals 1 over 1 minus x, sum j and x, x to the j. These are these numerators of our generating functions, and we have a stick with the elements of a, that are not in a cyclotomic set. When S is a finite subset of the positive integers, even when S is not a cyclotomic set, they seem to have a lot of zeros on the unit circle. If S is a cyclotomic set, of course, all the zeros are roots of unity, so are on the unit circle. But even when for general S, an amazing number of zeros appear on the unit circle. When the maximum S is 2m plus 1, there's 2 to the m such polynomials, that are palindromic and are of this form. And for instance, when n equals 33, you look at all these polynomials, 2 to the 16th of them, that is 65,536. The proportion of zeros on the unit circle is almost 69% of all of their, or that is almost 70% of all of their zeros are on the unit circle. I don't have a reason for this. No one who responded to this Math Overflow question came up with a good reason. I think that's an interesting problem to look at. Now, let me talk about cleanness. This is this property for when the numerator canceled the denominator and the denominator had factors only with multiplicity 1. So first I'll note that if we have a formal power series with constant term 1, you can always formally write it in the form product n greater than or equal to 1 minus x to the n to the minus an. This is easy to show by induction. Once we've chosen a1 up to an minus 1, looking at the coefficient of x to the n on both sides here determines an uniquely. So if we have our subset S of the positive integers, and our f of x equals 1 over 1 minus x minus the sum of the element x to the j, where j is an S, we'll say S is clean if f of x squared, f of x cubed, etc. As this is a product of 1 minus x to the n to the minus an, and that is, we write it uniquely in this form, and we want each an to be 0 or 1. Then we're going to get a clean partition identity. The partitions whose part multiplicities are not in S are equal to numbers whose parts are these ANs equal to 1. So this is the second nice property of S that gave us very elegant partition identities like McMahon's. Not every cyclotomic set is clean. For instance, for this example, 1, 5, 7, 8, 9, 11, this is cyclotomic, but when we form this product, f of x squared, f of x cubed, and reduce it, divide out all the common factors from numerator and denominator, we're left with this. So we're going to get some kind of partition identity, but it's going to be messy because of this numerator. We're going to have parts that part multiplicities can appear at most once, but they weighted by some -1 to some power. And for some other values of S, we can have exponents in the numerator greater than 1. So we have to color the parts with different colors. Well, I don't have a nice theory of clean sets. There's some infinite classes I know, but otherwise you have to just take your cyclotomic set and check by brute force whether it's clean. Well, what is a situation in which cyclotomic sets occur? Well, they've shown up in the theory of numerical semigroups. By definition, a numerical semigroup, it really should be called a numerical monoid, but this is the standard terminology. A numerical semigroup is a submonoid M of the natural numbers, the non-negative integers, under addition, such that n minus m is finite. So we have a subset of the non-negative integers, only finitely many missing numbers, and it has to be closed under addition. Well, it contains 0, because a monoid has an identity element. Well, it's well known that every submonoid of the non-negative integer, well, it's either 0 or is a positive multiple of a numerical semigroup. We can just divide all the elements by the GCD and get a numerical semigroup. We really don't have any loss of generality by restricting our attention to numerical semigroups rather than any submonoid. Also, it's well known that every submonoid of n is finitely generated. This is not true, for instance, for n squared, but it's true for n. So let's look at the generating function for elements of m, a_m of x. The sum over I and m, x to the I. We could also call this a Hilbert series of m. So it's just 1 over 1 minus x minus the sum of the elements that are not in m. That is I in n minus m, which is finite. So we're taking 1 over 1 minus x and subtracting finitely many terms. Well, this person, Chiolin and collaborators, defined a numerical semigroup to be cyclotomic if 1 over 1 minus x times a_m of x, we just clear this denominator, is a product of cyclotomic polynomials. So that's exactly the same as saying that n minus m, the elements missing from our monoid, form a cyclotomic set. For instance, if m is generated by 2 elements, so I'll use this angle bracket notation for generators, where a and b are greater than or equal to 2, and their GCD is 1, so I have a numerical semigroup. Only finitely many elements are missing from when the generators are 2 elements. Then one can compute the generating function for the elements of m is this very simple form, 1 over x to the ab over 1 minus x to the a, 1 minus x to the b. Of course, well, this is of the form of product of 1 minus x to the ai's, where ai is some integer. So that means m is a cyclotomic semigroup. Well, or in other words, these factors are products of cyclotomic polynomials. So for instance, so this gives a whole infinite class of numerical semigroups, those generated that are cyclotomic, those generated by 2 elements. And it also turns out it's easy to see that they're clean. A and B are relatively prime, so in the numerator, when we look at the product of AM of x1, AM of x2, etc. We'll get as exponents all the multiples of A and B, with the multiples A, B appearing twice. One of those get canceled out by 1 over this x to the AB, the numerator factors, exactly as in McMahon's theorem. So we're going to have a nice partition identity for every such pair. What about 3 generators? Well, if we look at the generators 4, 6, and 7, the missing elements turn out to be 1, 2, 3, 5, 9. And this is a cyclotomic semigroup. But for 5, 6, 7, it's not cyclotomic. So sometimes it is, sometimes it isn't. We say more. Well, we have a following. I should first go back to AB being cyclotomic. Since this monoid with 2 generators is cyclotomic and clean, we're going to get a nice partition identity, and it's this identity. If A, B are greater than or equal to 2, and the GCD of A and B is 1, then the number of partitions of N whose part multiplicities belong to the monoid generated by A and B is the number of partitions of N into parts divisible by A or B. Okay, now let's try to get some commutative algebra into the picture. It turns out to be a very natural tool for this subject. So the semigroup algebra, which I denote by Km over a field K of a numerical semigroup, we can just define to be the ring of polynomials generated by, or actually equal to z to the I, for I and M. So all the polynomials over K, whose terms z to the I satisfy that I is an M. This monoid, if M is generated by A1 up to AR, then M will be generated by Z to the A1 up to Z to the AR. And we say, and this is a definition from commutative algebra, that M is a complete intersection if all the relations among the generators Z to the A1 up to Z to the AR are consequences of only R minus one of them. This is the minimum possible number of generators, number of relations. We have R generators, and we want the minimum number of relations, R minus one. By elementary commutative algebra, we can compute the, well, if we have a complete intersection, in a more general situation, the Hilbert series will be a product of 1 minus x to the AIs, and therefore, in this situation, if Km is a complete intersection, M is cyclotomic. So cyclotomic, a complete intersection semigroup algebras will give us cyclotomic semigroups. And the main open problem on cyclotomic numerical semigroups is the converse. If we have a cyclotomic numerical semigroup, is this semigroup algebra a complete intersection? Here's an example. Let's say the generators of M are 4, 6, and 7. So this is a numerical semigroup. The missing elements are 1, 2, 3, 5, and 9. The conditions of being a numerical semigroup are that the GCD of all the generators is 1. So the generators of the semigroup algebra are Z to the 4th, Z to the 6th, Z to the 7th. Of corresponding to the generators 4, 6, 7 of M. Well, there's infinitely many relations among these generators. A cubed equals B squared, right? It corresponds, numerically to 3 times 4 equals 2 times 6. A squared B equals C squared. 2 times 4 plus 6 equals 2 times 7. 7. B to the 7th equals C to the 4th. B to the 7th equals C to the 6th. Infinitely many, but they're all consequences of the first two. For instance, to get this relation C to the 4th equals A to the 7th, we'll take C to the 4th. Well, C squared is A squared B, so this is A squared B squared, which is A to the 4th B squared. But A cubed to our B squared, we can replace by A cubed. So we'll get A to the 4th A cubed, which is A to the 7th. So this, we get the relation C to the 4th A to the 7th. It's a consequence of the first two. But all of the relations are a consequence of the first two. So we have a complete intersection. The degree of the relation A cubed equals B squared is 12, like the polynomial A cubed is C to the 12th, which has degree 12. Similarly, the degree of the second relation is 14. And by the theory of complete intersections, that means this Hilbert series is in the numerator, we're going to get the degrees of the relations, 1 minus x to the 12th, 1 minus x to the 14th, and the denominator, the degrees of the generators, 4, 6, and 7. So we do have a cyclotomic set. 1, 2, 3, 5, 9. That was because we had a complete intersection. Let's look at a non-example. That is a non-complete intersection generated by 14, 13, and 23. So the generators of this algebra are z to the 4th, z to the 13th, z to the 23. One can show, like using the Macaulay software, for instance, that we have 3 minimal relations. And these are what they are. So it's not a complete intersection. We want 2 minimal relations for a complete intersection. Well, you could challenge this. If we take the relation c squared equals a to the 5th, a to the 5th b, c to the c squared is a to the 5th b squared, multiplied by b, we'll get c squared b equals a to the 5th b cubed. Now for b cubed, we can substitute a to the 4th c in this relation. We'll get c squared b equals a to the 9th c here. Then just divide by c squared equals a to the 9th. We'll get this first relation. So it seems like I've gotten the first relation from these two. So why are the, why are the relations independent? Why can't we do this? And the answer is that we're not allowed to divide by c. When we talk about relations among the generators, I can only use the algebra operations, taking linear combinations and multiply, not divide. So this is not allowed. These are the actual minimal relations. Oh, very interesting. If Herzog from 1969 is related to numerical semigroups with 3 generators, A, B, and C. The following are equivalent. This semigroup algebra is a complete intersection. M is a cyclotomic semigroup. So this was open in general. The main open problem was whether cyclotomic implied a complete intersection. It is true for 3 generators, and even a much weaker condition is true Thus, all you need is that this numerator polynomial is symmetric, palindromic. Remember, in general, that was far from true. You had many exponential number of symmetric polynomials with a given maximum element D of S, but around linear, a number of them, cyclotomic. And for people who know commutative algebra, this is also equivalent, turns out to be equivalent to M being, to K of M being a Gorenstein, which in general is weaker than being completely section. So our main open problem on cyclotomic numerical semigroups is true for 3 generators. So an open problem which may be tractable, even if you can't prove the main open problem, I think it may be possible to describe all the numerical semigroups for which the semigroup algebra is a complete intersection. Okay, so let's try to generalize this technique I use for getting partition identity to other contexts. So I recall my definition of a cyclotomic set, and I want to extend this definition, this phenomenon here, where this identity yielded products of cyclotomic polynomials. I want to extend this to other situations. I could give a very general result, but it's kind of abstract, a little hard to absorb. So instead I'll just give 2 special cases of polynomials over finite fields in Dirichlet series. So for polynomial over finite fields, let's fix a prime power Q. We're going to be dealing with the finite field FQ. Beta n will be the number of monic irreducible polynomials of degree n. There is a formula for beta n, but it's irrelevant for what I'm going to do. There are q to the n monic polynomials of degree n over fq, right? There's n minus 1 coefficients, which can be anything in the field. And then the leading coefficient is 1. Every such polynomial is unique product up to order of monic irreducible polynomials. And then we're going to get this well-known identity, the generating function for all the monic polynomials of degree n, q to the n of them. So it's just 1 over 1 minus qx. We can get a monic polynomial by choosing the degree of the polynomial, 1 minus x to the m. We have beta m choices for which irreducible polynomial we choose. And then 1 minus x to the m inverse, the expansion of that chooses the multiplicity of that irreducible polynomial. Here we get this well-known identity. It's just the analytic way of expressing the unique factorization property of polynomials over a field. Polynomials in one variable over a field. Well, let's try to compute, as an example of my technique, the number of irreducible polynomials that are monic and of degree n over fq, such that every irreducible factor has multiplicity at least 2. These are called powerful polynomials. No irreducible factor has multiplicity 1. Well, just like we did for getting partition identities, our generating function for f of n, the number of monic powerful polynomials of degree n, will be this product, 1 plus x to the 1 plus 1 x to the 2m, x to the 3m, etc. But instead of this exponent being just 1 as for partition identities, it's beta m, the number of irreducible polynomials of degree m. Okay? For each irreducible polynomial, we choose a term here, the multiplicity of that irreducible polynomial. It cannot be x to the m because the definition of powerful multiplicity 1 is not allowed. And then we do this for beta m different irreducible polynomials. So this is a generating function for f of n. And we're in familiar territory with this sum we saw before. It's 1 minus x to the 6m, 1 minus x to the 2m, 1 minus x to the 3m. And now we just have to apply this identity, but with x replaced by x squared, x cubed, and x to the 6th. And we're going to we apply it to this factor, and this factor. And this just equals 1 minus q x to the 6th, 1 minus q x squared, 1 minus q x cubed. A very simple explicit formula for this generating function. Now we can do more. We can easily extract the coefficient of f of n, of x to the n, by expanding in a partial fraction to respect to q. We get this as a partial fraction expansion, and we can multiply it out, and because of this x squared and x cubed in the denominator, we're going to get an expression for f of n that depends on n mod 6. And it's just kind of a nice accident here that it reduces this very simple expression. Very simple explicit formula involving the integer part function. So this is the exact analog of McMahon's theorem for partitions with no part appearing exactly once. Polynomials with no factor having multiplicity of 1. This easily generalizes for any cyclotomic set. So any cyclotomic subset of P, you look at this sum, 1 minus x, 1 over 1 minus x minus x to the I and s. Because it's cyclotomic, we can write it in this product form. And by exactly the same argument I just did for powerful polynomials, if f of n is a number of monic irreducible polynomials of degree n over x, such that no irreducible factor has multiplicity appearing in S, then the generating function for f of n is this product. This is a finite product. We can expand by partial fractions with respect to q, and we can always get some kind of formula for f of n involving congruence classes modulo some number. Here's what it looks like for the cyclotomic set 1, 2, 3, 5, 7, and 11. The generating function is this. This should look familiar because when you set q equals to 1, this was what we'll, so, look at the product of this, of substitute x to the I for x and look at the product over all xi. We got this is exactly what I looked at before as when I looked at partition identities. The expansion, partial fraction expansion with respect to q is this. Or by pj, I mean the pj of x. Well, I didn't bother working it out, but you can get a formula for f of n that depends on the congruence class of n mod 36. I'm looking at irreducible polynomials, degree n, with no part multiplicity. I mean, no factor appearing with multiplicity 1, 2, 3, 5, 7, or 11. Another example, the one that gave Euler's formula, where partitions into distinct parts and odd parts. Well, if you work that out, there's a generating function. Remember, the numerator corresponds to, well, there's always 1 minus qx in the denominator. Corresponds to, what am I saying? Well, we have to go back to the original formula. But this corresponds to partitions into distinct parts when we looked at partitions. Here, it's 1 over 1 minus qx squared over 1 minus qx, and it has the expansion where the coefficient of x to the n is q minus 1, q to the n minus 1. So that's the number of square-free monic polynomials of degree n over fq. This was a well-known fact, but it fits nicely into my setup. It's a kind of FQ analog of Euler's formula about partitions as distinct parts and odd parts. It's not a Q analog in the normal sense. If you set Q equal to 1 here, you don't get what we want, the partition identity you want. You have to look at a product where you substitute x to the I for x. But it is some kind of a finite field analog of Euler's formula. And finally, we can look at my last example, factorization of integers. All that we really use about polynomials was unique factorization. Well, Z, the integers, have unique factorization. Can they be put into this setup? Well, the correct kind of generating function we want to use are Dirichlet series. The Dirichlet series generating function for f of n, where n is a positive integer, is the sum of f of n to the minus s. When f of n is 1, we get the Riemann zeta function, which has this product expansion, which goes back to Euler. It's the analytic way of writing the unique factorization of integers. Well, let's look at powerful numbers instead of powerful polynomials. A powerful number is a number that when you factor into primes, every factor appears at least twice. No prime factor appears exactly once. So with this definition, 1 is a powerful number. We're interested in just looking at the Dirichlet series generating function for powerful numbers, the sum over n to the minus s, where n is powerful. So it's just this product, basically, because powerful numbers are determined by what happens with each prime factor separately. This is saying the prime factors can appear with multiplicity 0, 2, 3, 4. 1 is not allowed. Exactly the same kind of manipulation as for partitions and polynomials over FQ. This sum is equal to 1 over 1 minus p to the minus s minus p to the minus s, which has this nice alternative, simplification. And we now just apply the identity for the Riemann zeta function, where s is replaced by 2s, 3s, and 6s. Then we get zeta 2s, zeta 3s over zeta 6s, with this generating function for powerful numbers. This has been known for quite a while. As a kind of insignificant corollary, we know the values of zeta 4, zeta 6, and zeta 12. So if you stick s equal to 1 in this expansion, we'll get here the sum of the reciprocals of the squares of the powerful numbers, zeta 2, zeta 4, zeta 6, zeta 12, substituting s equals 2, which is 15,015 over 1,382 pi squared, which is about 1.1. Well, you can see we can now play this game for other cyclotomic sets, get nice generating functions for their corresponding integers that avoid these part multiplicities or prime power multiplicities, get crazy identities like this. It's a nice, the cyclotomic technique, you might say, has a lot of interesting applications. In general, with these Dirichlet series, if we take our cyclotomic set and write this sum as this finite product, which is equivalent to being cyclotomic, then the generating function for all n, such that when we look at a prime power factorization, no prime power appears with multiplicity m in S. It's exactly this zeta function, a finite zeta function product. Okay, that's what I wanted to say. So thank you for listening.